and thanks to the organizers for the opportunity to give this talk. So yes, this is a work at the interface of quantum gravity and quantum information, and in particular is a characterization of black hole-like regions via an information theoretic perspective. So let me start by giving some motivations on why working at the interface of quantum gravity and quantum information. So we expected the space-time at the Planck scale to dissolve into a microstructure of fundamental quantum entities. So in this atomistic picture of space-time at the Planck scale, we expect continuum space-time and geometry to be reconstructed from the quantum correlations, in particular entanglement of these pre-geometric quantum entities. In this view, space-time is therefore described as a quantum many-body system with the peculiarity of being background independent, meaning that it is not a many-body system embedded in space and time, but it is space-time in itself. So the main goal of the quantum gravity approaches which share this view is to extract continuum physics, continuum space-time and geometry from the collective behavior of these pre-geometric quantum entities. And so you can see why quantum information and condensed matter tools can help us carrying out this emergent space-time program. So we have several results supporting this connection between gravity and entanglement. So in particular, entanglement seems to be at the origin of space-time connectivity, but we have evidence of the possibility to reconstruct special geometries even in contexts not directly related to quantum gravity. And in this scenario of results at the interface of quantum gravity and quantum information, gravity and entanglement also turn out to be deeply tied with another concept which is crucial in quantum gravity, which is holography. Holography is the idea that the physics of a certain region of space can be fully encoded in the boundary of that region. Holography has played a central role in quantum gravity research. The holographic principle was first formulated following the discovery of the Bekenstein-Hawking area law for black hole entropy. And then one of the main example of holography in quantum gravity is the anti-de Sitter conformal field theory correspondence, which is a duality between the gravitational physics of a space-time with anti-de Sitter boundary conditions and conformal field theory living on the boundary. So in general, gravity exhibits an holographic behavior in several contexts. But to close the circle, we have that holography is also deeply tied to entanglement in several quantum information and condensed matter models. So in particular, we know that many body systems in their ground state satisfy area laws. But we also have example of holographic models through quantum error correcting codes. So we have evidence of this, threefold connection, and understanding the origin of this threefold connection can help us constructing a theory of quantum gravity, which is a major challenge in theoretical physics. So the work I'm presenting today sits in this framework. So in particular, we started from a characterization of a quantum gravity language in terms of a quantum information one. So the quantum gravity language is that of spin networks. Spin networks are graphs decorated by some geometric data, which are dual to discrete geometries. So in particular, we have an elementary portion of space dual to each vertex. These portions of space are glued to each other to form discrete geometries, and the dual picture is that of a graph decorated by quantum data. And so we characterize these spin network states, which are kinematical states of several quantum gravity approaches. They are mainly known to be the kinematical states of loop quantum gravity, but they also enter spin-foam models, which is the covariant counterpart of loop quantum gravity, and group field theory, which is a sort of second quantization of loop quantum gravity. So we characterize these spin network states in terms of patterns of entanglement among the space quanta, and we put in correspondence with tensor networks. By relying on this characterization, we then investigated holography for spatial regions modeled by spin networks, and we follow two approaches. So the first one is so given a portion of space modeled by spin networks to study the flow of information from the bulk to the boundary. And we did this via the Choi-Miolkowski dualism, and we studied the properties of the quantum channels mapping the bulk geometric data to the boundary ones, and we studied under which conditions this flow of information is holographic. So the data are isometrically mapped from the bulk to the boundary. But the talk that I'm giving today is focused on this second direction, which is, so given, as before, a certain region of space modeled by a spin network, to look at the boundary entropy and study how the boundary is affected by the bulk. So which information on the bulk we can recover from the boundary. And in particular, as I'm going to illustrate, by increasing the entanglement content of a certain region of the bulk, we achieve a regime in which this region behaves like a black hole, meaning that from the boundary we cannot get information about it. And so we tackle these two directions by exploiting the tensor network characterization, and in particular random tensor network techniques, thanks to which we map the computation of the entropy to an Ising model living on the spin network graphs themselves. Okay, so I'm illustrating in more detail the spin network formalism for quantum spacetime. So consider an elementary portion of space, which is a tetrahedron. Now, the classical geometry of a tetrahedron can be described by giving four vectors, each one normal to a face of the tetrahedron and with length equal to the face area. Now, for these four vectors to properly describe the geometry of a tetrahedron, they have to sum to 0. So we have this additional condition. And if we quantize the phase space of geometries of this tetrahedron, we end up with an Hilbert space, which is describing 4 spins, one for each face of the tetrahedron, and the value of the spins turns out to be related to the area of the face of the tetrahedron. And then we have an additional degree of freedom, which comes from this closure condition, which is in the canonical quantization of general relativity, the Gauss constraint. And so it's the constraint imposing the gauge invariance at each vertex. And so we have this additional quantum number called intertwiner, which is related to the volume of the tetrahedron. So we have, at the quantum level, this fuzzy tetrahedron, and we can use a dual picture for it, in which we have a vertex and 4 links, each one dual to a face, and the intertwiner quantum number is attached to the core of this vertex. The spins are attached to the 4 links, and at the endpoints, the 3 endpoints of the links, we have the magnetic numbers for the spin states. So this is a spin network vertex describing a quantum tetrahedron. Now, spin networks, as I mentioned before, are discrete geometries built up from gluing this elementary portion of space. And so in the dual representation, by gluing together vertices dual to the individual tetrahedra, we get a graph. And this is the spin network graph with the spins attached to the links, the intertwiners attached to the nodes, and the magnetic indices on the open links. I also mentioned that they enter several approaches to quantum gravity. The main one is loop quantum gravity, which is a quantization, a canonical quantization of general relativity, and corresponds to writing general relativity as a gauge theory. Then we have the covariant counterpart spin-foam models, and then we have group field theory, which is the approach we work on, which can be understood as a second quantization of loop quantum gravity. So in group field theory is understood as a quantum field theory of spacetime, in the sense that the fundamental excitations of the field are understood as quanta of space, so as the tetrahedra dual to the spin network vertices. Okay, so so let me illustrate this characterization of spin networks as patterns of entanglement, and therefore as tensor networks. So in group field theory, we have a Fock space describing this fuzzy tetrahedra, this quantum tetrahedra. So a generic wave function in the Fock space is a wave function describing a generic set of individual atoms of space, the individual tetrahedra. The gluing of these tetrahedra to each other is realized by entangling the edge degrees of freedom of the vertices. So here we have the projection of the many-body wave function to link states, which are maximally entangled states of the degrees of freedom attached to the edges. So thanks to this gluing, which corresponds to the entanglement of the edge degrees of freedom, we end up with a state which is a pattern of entanglement among the space quanta, and therefore a spin network wave function for the graph with the combinatorial pattern we use to glue the vertices. So in this view, the gluing of the individual vertices is given by entanglement. If we start instead that from a generic vertex, generic wave function for the vertices from a state that factorizes per vertex, so in this case we have the wave function f for each vertex, and then perform the gluing I mentioned before, the final state corresponds to generalized tensor networks. So we see that the wave function is just a set of tensors, one for each vertex, contracted according to a certain pattern, and the pattern is exactly the spin network graph. So in particular, they correspond to what are called project entangled per states. In fact, we started from individual states and projected into maximally entangled states. Note that what is understood as a physical index in tensor networks, in this case, is the intertwiner degrees of freedom, while the indices which are contracted to each other and form the network, namely the spin network graph, are the magnetic indices associated to the open links. And finally, the spins, which are related to the area of the surfaces dual to the elementary links, are the bond dimensions of our tensor network. So we have tensor networks generalized in several aspects. So first of all, in the quantum gravity context of group field theory, all dimensions are dynamical variables. So bond dimensions are not fixed as in usual tensor networks. And also we have a dependence of the physical index from the auxiliary ones, which is also something not usually considered in tensor networks. But more importantly, since we are in a second quantized setting, so these states are embedded in a Fock space, so first of all, we have some symmetric properties of these states because the individual nodes, the individual vertices are undistinguishable. And also the combinatorial structure, so the network is dynamical. So we are creating and destroying individual vertices. So everything in this context is dynamical. So, so far I described the basis of our work, so the preliminary step. Now I'm moving to the investigation of holography. So I mentioned before that the idea is considering a certain region of space modeled by a spin network and study how the entropy of the boundary is related to the bulk. So in our context, the bulk degrees of freedom are the intertwiners, so the degrees of freedom encoding the volume quantum numbers. And the boundary degrees of freedom are the spins living on the open links of the spin network. So we focus on the class of spin network states I introduced before, corresponding to tensor networks. In particular, we consider a random distribution for the individual vertex wave functions so that our states are effectively random tensor networks. And we also establish some correlations among the intertwiner degrees of freedom by projecting the state into a certain state for the intertwiners, so for the bulk. The main tool for the computation of the entropy is what I mentioned at the beginning, the mapping of the computation to the evaluation of the free energy of an Ising model. So it works like that. We focused on the second order Rényi entropy, and since the wave functions for the vertices are randomly distributed, we look at the average value for the entropy. And we compute it by using the replica trick that many of you probably know is a trick to compute the partial trace of a generic state. And the idea is that we take two copies of the parent state, and then we have a swapping operator, which is swapping just the region, the degrees of freedom of the portion of the space we want to probe. So in this case, we have this generic spin network described by a tensor network, and we want to compute the entanglement entropy of this boundary region A. So if the state is the one I described before, via the replica trick, we have two copies of this bulk input state, two copies for each maximally entangled state for the link, two copies of each state for the vertices, and then the swapping operator on the region A of the boundary. And the main step of the computation is computing the average value over the vertex wave functions. Via the Schur's lemma, we obtain a sum over the identity operator and a swapping operator for the individual vertex. And we can model the presence of one or the other in the trace by introducing a two-level variable that is going to play the role of an Ising spin. In fact, the computation is a bit involved, but the result is that this trace can be written as a partition function for an Ising model, and here we have the Ising action. And you can see that, so for each vertex of the spin network, we have an Ising spin, and the nearest neighbor Ising spins are interacting to each other, and the strength of interaction depends on the dimension of the link connecting them. And here we have the Ising spins interacting with additional variables called the pinning fields, which are living on the boundary, are depicted in red here, and coming from the swapping operator of the replica trick. And then we have a contribution for the entropy of the bulk state. So the main point here is that you get an Ising model living on the spin network graph itself. And so to compute the entropy, we just need to analyze this model and see which configuration minimizes the energy. So let me start with the homogeneous case, which is particularly simple. In the homogeneous case, all links carry the same spin, so the couplings are the same for the Ising model. And the Hamiltonian, the Ising Hamiltonian takes this simple form. In particular, we can identify this parameter, the logarithm of the dimension of the link, which plays the role of inverse Ising temperature. So this is the partition function through which we can compute the entropy. And this is the Hamiltonian. And the Ising Hamiltonian has this contribution which just corresponds to the area of the domain wall separating the spin up and the spin down region in the Ising model. So here we have an example. These in red are the pinning fields, which are flipped down just in the region A we want to probe. And here we have the two regions of the Ising spins which settle down in order to minimize the area of this surface. And this contribution is exactly the area as every pair of misaligned spins carries a contribution +1 to this Hamiltonian. So we are just counting the links which are crossed by this domain wall. We work in the I-spins regime to minimize the uncertainty on the average values we are computing. And so we can derive an holographic regime where the correction coming from the bulk entanglement is small compared to this area term. And so we just get an area law for the boundary entropy. Of course, we also have the opposite regime in which the contribution from the bulk is not small compared to this area term, and so we have to take into account to minimize not only the area of this surface, but also the content, the entanglement content of this region. So here we have an example. So we have here a specific spin network graph. So we consider the case in which the entanglement entropy is present only in a certain region, omega, of the bulk, for which we use the random pure states. And so we could compute the average value of the entropy. And we see that the volume contribution is just the minimum number of vertices on one side or the other. But the more interesting picture is the one in which we increase the entanglement content of the bulk, and so we reach a regime in which the domain wall, the Ising domain wall, is prevented from entering this region. So this region is effectively behaving like a black hole-like region. So by probing the entanglement entropy of the boundary, we cannot get information from heat. The inhomogeneous case is very similar. The only difference is that the couplings of the Ising model are now are not the same for the graph. So every link has its own dimension. So, but still we have a contribution given by the area of the domain wall. It's just that when computing the area, we have to take into account that every link is weighted differently. And the example in this case, we consider a spherically symmetric geometry in which we have the spins, which corresponds to the area of the surfaces dual to the links are increasing with the radius, so as we expect for spherical geometry. And the picture is the following. So when we assume that there is no entanglement in the bulk, the Ising domain wall just drops towards the most inner shell. But if we switch on the entanglement into a certain disk of the bulk, the Ising domain wall just stops before this region. And so again, we obtain something that behaves like a black hole. Okay, so let me summarize. The idea is that if we want to study the quantum nature of space-time, we expect it to be composed of fundamental quantum entities at the Planck scale, and so we want to extract continuum physics from the collective behavior of these entities. We need to import techniques from condensed matter physics and quantum information. And to carry out this program, we just characterized the quantum gravity language of spin networks in terms of tensor networks, which are very effective in modeling the entanglement of many body systems. And in particular, they allowed us to map the entropy computation of arbitrary complicated graph to the evaluation of the free energy of an Ising model. And through this tool, we are able to study the holographic features of regions of space modeled by spin networks and characterize the behavior of bulk regions that effectively behaves like black hole. This analysis was just at the kinematic level, so we are now working to promote it to the dynamic level, and there are several steps. Of course, the first one that we already carried out together with Simon Langenscheidt and Daniele Oriti is generalize these results to the superposition of networks with different assignment of the spins on the links. The next step will be to consider superposition of different graphs because, as I said, the combinatorial structure of this network is dynamical, so we expect physical states to be a superposition of different geometries. And then connect to other results on the holographic behavior of spin networks, and I mentioned here some recent directions in loop quantum gravity. And maybe I'm out of time. Okay, thank you.
So thank you very much about this fascinating report connecting tensor networks and quantum gravity. Are there questions? Yes, please.
Thank you for your work, but I have a question about the bulk state. Does your research have any sense about the thermalization of the bulk state? And one more question is that what happened by increasing the size of the bulk state to the system?
By increasing the bulk?
The size of the bulk.
Okay, so So about the first question, well, we consider a very the generic case of a random pure state to be able to get the exact expression for the entropy, but we didn't check the thermalization, but actually this is something I listed, I think, in the Outlook, because there are several results, in particular this one by Kirko and Anza, which is related to this thermalization effect for black hole region in a spin network, but it's something we didn't look at. And by increasing the size of the bulk, this is exactly what switch on this black hole-like behavior. Now, in the case of the homogeneous spin network, we can increase the entanglement, the dimension of the bulk, and so the entanglement content it can have by adding vertices. So in this case, this is the only parameter we can control. In this case, where we have an inhomogeneous geometries, in particular here, by increasing the spins, the increase of the dimension is controlled by the dimension of the spins. But so in both cases, by increasing the dimension of the bulk, assuming that the bulk is in a random pure state, and so that we have if we have entanglement in that region, this is what triggers this black hole effect.
Okay, any more questions? Actually, I have a quick question. Are you bothered by the prospect of spin glass appearing and replica symmetry breaking, which I understand you're presupposing that it doesn't occur?
Well, no, so at the beginning we thought that we were getting something like a spin glass from this picture, but actually I don't know much about spin glasses, so maybe I'm wrong, but the fact is that the couplings of our model are always positive, so we cannot really get the spin glass effect on these networks. This is what we...
Because you assumed the replica trick to work a priori, no?
Yes.
That might be a problem.
Okay. Okay.
Here is another.
So I would go for one, yes. Hi. So I apologize if this is a stupid question. I'm an experimental condensed matter physicist, and I was wondering to what extent you can benchmark these considerations and models against real condensed matter systems. So how far is this removed, basically, from, or it feels like you may be able to perhaps even say something about a simplified version about real materials or real systems?
Well, of course, these are really like toy models, at least the one we explored. But so the idea is that actually these models are not really dependent on the specific connectivity of the network, because since we are looking at random vertex wave functions, in a certain sense, the role of the connectivity here is so it is not the first. So what really triggers this effect are just the random nature of the vertices. So we expect this to actually be to work also when we consider a huge number of vertices and. But we, in fact, one of the directions we want to explore is to apply these to condensate states for cosmology, to try to say something more about more realistic geometries useful for cosmology. This is just really at the fundamental level. So as far as we just consider toy models like these, of course, is not... So just to have an hint of what is going on, depending on the entanglement of the degrees of freedom, what is the effect that we can trigger by changing the parameters of these spin network states.
Okay, maybe in the interest of time, let's postpone all further questions with a more private setup. And let us thank Eugenia again for this very nice talk.
Thank you.